This is lecture 28 on urban transportation planning. We will continue our discussion on route assignment in this lecture. You may recall that we discussed about three important aspects related to route assignment in the previous lecture. The first important point was with regard to conversion of person trips into vehicular trips. The key to that is the information about the average vehicle ownership of different categories of vehicles that we come across in an urban area. That information is used to convert person trips into equivalent vehicular trips of different categories. Second important aspect is about, why don't you use the microphone please?
Temporal variation of vehicles during the day.
Temporal variation of demand for travel in general. So far, or in the first three steps, we were dealing with full day travel demand, 24 hours traffic, whereas in a real life situation the demand varies over a period of time. So we need to account for temporal variation of the demand for transportation. In that context, we discussed about assigning trips separately for morning peak, evening peak and during non-peak hours. And finally, the third important point that we discussed about was with regard to direction of movement of traffic. That is very important because ultimately we need to predict the actual traffic flow in the whole of the network after completing the assignment. So that is how the direction of movement is also an important factor. After discussion of these three important aspects, we try to understand representation of the road network in the form of nodes and links. And now we know we can represent the road network using just a set of numbers. Numbers will directly indicate the nodes, and the two numbers related to two nodes at the end of a road stretch can be used to designate a link, isn't it? That is how we have understood representing road network using nodes and links. And this is the traffic zone that we considered as an example in the previous class, and the zone boundary was given like this, and the coded road network for this case, as you may recall, is this. We have ignored some of the minor roads, only major roads have been considered, and all the points of intersections of the roads are given numbers which are node numbers. And now we can represent any intersection using these numbers, and any stretch of road can be represented using a set of numbers. For example, 315, 316 refers to the stretch of road connecting the nodes 315 and 316. Clear? So that is the advantage of giving node numbers and then expressing nodes and links using these numbers. And each node, as we know, is specified by a numerical code as we have seen, and each link is described by its end nodes 315, 316 as I told you. And it would be possible to indicate the type of a link by appropriate choice of node numbers. What do you understand by type of link? We may have different categories of roads in major urban areas. Arterials, subarterials, in certain cases even expressways, as in the case of developed countries. It is possible by appropriate numbering of these nodes to give an indication of the type of link, or you will be able to know whether the link pertains to an arterial or subarterial or an expressway. That is also possible. So that will give a better perception of things when you look at the link and node numbers, right. How do we do that? For example, nodes that lie exclusively on arterial streets may be denoted by one range of numerical codes, say between 100 and 1000. So whenever we come across node numbers in this range, we will realize that this node pertains to arterial, right. You fix a range, you know the total number of nodes in an urban area. Knowing the total number, you can always fix a range, right. Whereas nodes that lie on higher type of facilities, say expressway, may be coded with numbers in another range, say greater than 1000. So whenever your node number is more than 1000, you can have a feel of that node, and you can understand that this node pertains to expressway, not an arterial. Clear? Thus a link connecting nodes 525 and 666 is clearly a segment of an arterial street, is not it? It is lying in the range of 100 to 1000, whereas a link with node numbers 1212 and 1213 is a segment of a freeway, because the value is more than 1000, is not it? We are not looking at the network map, we are looking at the numbers, still we are able to perceive the type of link because of this methodology of giving numbers for the nodes, right. Another interesting aspect is this: links 729 1432 and 1198 888 represent an on ramp. On ramps are the ramps which take the traffic from the ground level to a higher level in the case of grade separated intersections. Please remember, the expressways will have all its intersections grade separated, okay. Otherwise it cannot be called as an expressway. There will not be any interruption of cross traffic as far as an expressway is concerned. When you grade separate all the intersections, the flow will be free, right. So when you try to connect an arterial to an expressway, there need to be a ramp connection from ground level to a higher level, clear. So that is how you must understand the numbers given here. 729 1432 means from arterial to expressway. This refers to an on ramp going on to the expressway from arterial to expressway, and an off ramp is having the number 1198 and 888 888 from the expressway to the arterial, right. So we are not referring to your intersection layout, we just look at the numbers, still we are able to perceive whether it is an on ramp or off ramp and so on. So that is the advantage of planning your numbering process and then giving appropriate numbers for the nodes in the network, clear. Important characteristics of each link. What are the characteristics of links? Such as its capacity. Link capacity is a very important factor, isn't it? What is the capacity? what is the maximum traffic volume a link can carry is a very important information. Free flow speed. What do you understand by free flow speed? As the term implies, when the traffic is flowing freely without any hindrance by the presence of other vehicles, what is the speed that can be maintained by vehicles on a particular stretch is what is indicated here as free flow speed, right, or travel time along each link by a particular mode is also another important characteristics of a link, right. Capacity, free flow speed, travel time, these are all link characteristics which are very relevant for planning purpose, right. And these information can also be given in addition to the node numbers to indicate nodes and links. So each link must have information with regard to these characteristics also. And then travel analysis zones are coded as a set of imaginary nodes, as I pointed out in the previous class. The zone centroids are also given or considered as nodes and given node numbers, right, that are referred to as zone centroids. To distinguish them from the actual networks or network nodes, they are usually designated by numerical codes at the lower range of positive integers, or in other words, you choose a range of numbers at a lower level to give numbers for zone centroids. They are also node, so that by looking at the number you can understand that this node is not a road intersection, it is a zone centroid. So fix the ranges for different categories, right. Their geographical location is often taken to coincide with the activity or population centroids of the zones they represent, hence their name. When we say zone centroid, it is not the geometric center of traffic zones, it is the center of activity if it is a non-residential zone, or the center of the spread of population if it is a residential zone, right. And your activities may be spread unevenly in a particular zone, concentrated only on one half, the other half may be relatively less concentrated. Then your zone centroid will be shifted towards the more intense part of your zone, right. It will be eccentric physically, but it will be representative of the centroid of the activities, okay. And similarly, if the population concentration is more over one part of the traffic zone, then your centroid will shift towards that part, clear. So that when you assume that all the trips are emanating from that point, it should be more or less realistic, that is the idea. And finally, a set of imaginary links known as centroidal connectors are introduced to connect the zone centroids to the assignment network. That is important. When we give or when we consider zone centroids as nodes, then these nodes are to be connected to the main network, otherwise we will not be able to analyze the traffic flow and assign traffic, right. So we need to introduce imaginary links known as centroidal connectors to connect the zone centroids to the assignment network. Why imaginary links? Why not realistic links? Any response? Anyway, after a few seconds I will show you a picture which will depict the imaginary link, then we will be able to understand much better. Although not real links, they are typically given link attributes corresponding to the average conditions that trip makers experience on the non-coded local and minor street systems. There are several local minor streets which feed traffic onto the main roads. These imaginary links represent the traffic flow on all the minor roads within a traffic zone, right. You consider the same traffic zone here, and let us say where zone centroid is fixed in this area and given number 25 at the lower range, less than 100, right, and these two dotted lines connecting the adjoining road intersections, which are also nodal points with the zone centroid, are called dummy link to connect centroid to the main network, right. And this implies that we need to consider these dotted lines as real links with all link attributes for the purpose of route assignment, because we are going to assume that all the trips of this zone are emanating from that point, from 25. They have to move through the dotted lines and get connected to the main network. The reverse direction, they have to come from the main network through the dotted line into the traffic zone. And actually these trips may emanate from any part of the zone. There could be a set of trips from here and so on. Please note, we assume that all these trips together are emanating from only one point, right, and then we are just providing two links for connection to the main network. This implies that the travel time along this dummy link is a representative travel time experienced by the users of all the minor roads within the zone. Somebody living here may take about 2 minutes to reach this node. Somebody living in this area may take about 4 minutes to reach out this nodal point. Somebody here may take just 1 minute to reach out to this place, right. So the attribute or link travel time pertaining to this dummy link is the weighted average of the travel times related to all these movements, right. So that is how you need to understand the attributes of the dummy link. Clear? And you may wonder, why having two dummy links, why not only one, or why not more than two? Any response? Why not have less or more number of dummy links? Why only two? It depends on the actual traffic flow that we experience in the field. If the people living in this area are getting connected to all these intersections, all the 4 intersections evenly, then your links must represent the realistic flow condition, and you have to have more dummy links, and you must have connection from 25 to 315 as well as 318, right. And in this particular case you can assume that entry into this network is not possible for these people, and they have to get connected to the main network only through these two intersections. Under such condition we are just introducing only two dummy links. It represents the actual traffic flow in the field, and if connection to this node is prohibited, then we will have only one dummy link and everybody will be assumed to make use of only one path. Clear? There is one more aspect regarding the dummy link. Although not followed in this particular example that we saw, proper practice is to connect centroidal links or the dotted lines to dummy nodes along network links rather than directly to intersections. What is implied here is we should not connect the dummy link directly to the adjoining intersection, and we must connect it to the link adjoining link and then indirectly connect it to the intersection. That is a point made here, and we should know why we should do so. What is the problem? Any response? Why should we not connect zone centroid directly to the adjoining intersection? Think of the analysis of traffic flow at the intersection area. Let us say that particular intersection has got two intersecting roads. That means there will be 4 legs for the intersection or 4 approaches, and you are connecting one more dummy link to that intersection. That implies that you are introducing 5th approach to the intersection, isn't it, because you are connecting directly the zone centroid to the intersection. The physical meaning is you are adding one more approach to the intersection which is non-existent. The intersection has got only 4 approaches. Because of a manipulation, it gives an impression as far as analysis is concerned that the intersection is going to be treated as a 5-legged intersection, even though it is only a 4-legged intersection, which will give you erroneous results when you assign traffic, isn't it? You treat the intersection totally differently compared to the existing geometry of the intersection. How do we get over this problem? The solution is as indicated here. You just shift the dummy link to the intersection approach area, get it connected to the link, not directly to the node, and then the link will feed the traffic to the intersection. Clear? Then it will be more realistic. The reason, as I said, is to ensure that traffic flows on the centroidal connectors do not unrealistically load the intersections. The loading of the intersection will be unrealistic from non-existing approaches, right, and thus adversely affect subsequent level of service calculations. You are going to calculate delay at each of the intersections and so on. All these things are linked to the number of intersection approaches and the traffic on each of the approaches, right. So that is the reason why we should not connect the dummy links directly to the intersections. So this is the way we should do: shift the dummy links and connect them to the adjoining links, not directly to the nodes, and create dummy nodes again on the link, because any connecting point should have a node number. Since it is going to be practically connected to 316, have the same number and add one more alphabet, so that it gives a clear idea of why you are doing so and to which node it is really connected to. Clear? Similarly here, instead of 319 you name it as 319D. D stands for dummy. So this is how we need to give node numbers for network, particularly when you connect zone centroid. Clear? This is an example of a coded network, just to give you an idea of a fully coded network in the form of a picture. right. You have all the nodes numbered and link designations you can get from the node numbers, and the numbers in the parenthesis are the travel times in minutes along each of these links. How many zone centroids are involved in this example? There are 5 zone centroids, right, and how many centroidal connectors are involved? Yes, only one zone has got 2 centroidal connector. Zone 4 has got 2 connectors, right, and how many nodal points are involved in the main highway network? You can count and check, and you can also count the number of links involved, right. Okay. Now you can see the numbers in the parenthesis indicate the travel time on each of these links. Direction wise information is given. Is it necessary to give travel time information direction wise? When we say Sardar Patel Road, can we not give only one travel time? Why giving travel time information direction wise? Could it change based on the direction of movement? It can change because of what are the possible reasons for different travel times based on direction of movement. Let us say one direction of flow has got a relatively higher travel time. What could be the possibility or possible reason for the increase in travel time compared to the other direction of movement? Unless we are able to understand and appreciate the reason, we will not be that comfortable with the different numbers for different directions. Will it happen? It seems it is happening, and what are the possible reasons? Any response?
When the office goers are going towards one direction, is likely to be more congested and the travel time is likely to increase.
Yes, but normally for route assignment analysis we consider free flow travel time. So the effective traffic volume is not there, right. It is almost free flow travel time, and still there is difference in travel time based on the direction of movement. Any suggestion? Let us say there is a divided road, 4-lane divided roadway, right, and there could be crossroads connected to the main road that you consider, or crossroads connected to your link under consideration, right. On one side you may have 5 crossroads getting connected joining your link. On the other side there may not be any connection at all, it may be totally free. Then in that case the side which has got no connection will have least travel time because there is no interference from cross traffic, whereas from this side always there will be vehicles entering the mainstream, and the mainstream traffic has to slow down, adjust to the interference caused by the cross traffic, right. This is one possible reason. You can cite different types of examples. In another case, for example, one side of a road may have some institutional land use with very limited access, 1 or 2 entry points. The other side may have dense residential land use, right, with lot of entry points, as well as there is a need to restrict the speed because it is the residential land use, right. What is the normal way of restricting speed? They may introduce speed breakers at frequent intervals, or speed itself may be limited by installing speed limit signboards. In that case, on one side you can move fast, on the other side the speed is going to be much less. So practically these things can happen. Okay. So that is how we have to accept different numbers given for different directions of movement. For example, if you take link 7 8, 8 7 travel time is 6 minutes, whereas 7 8 travel time is only 4 minutes. There is a difference, significant difference, 6 minutes and 4 minutes. And there are few links which have same travel time implication on both the direction. It is possible when the conditions are similar, right. So let us try to summarize what we have discussed. So the simple network of the foregoing figure consists of 5 zonal centroids, right, that is nodes 1 to 5, 6 centroidal connectors because one zone centroid has got 2 connectors, 9 street intersections, right, that is nodes 6 to 14 and 13 arterial street links, 13 links are involved in that example. Please remember these values because we will be discussing about this network frequently to understand few other aspects related to assignment. The numerical values in parentheses correspond to the link impedances in the direction shown. We generally term it as link impedance, but in practice we take it as travel time. Link impedance means a different aspect, it is not simply travel time. This network is normally described by the link array table. As I told you in the previous class, we are not going to give this picture as input to the computer program for analysis, we have to deal with numbers only. So the same picture can be represented by a link array table, each cell of which represents a possible direct link between the row and the column nodes. A numerical entry in a cell means that there is in fact such a link first, then the cell value being say the link's impedance, possibly travel time. The dimensions of the link array may be increased to include other link attributes as well, such as free flow speed, length of the link itself and capacity of the link and so on. This is the link array table. It is not difficult to understand, make yourself comfortable, right, and I have just given numbers 1 to 14 along the row and 1 to 14 along the column. These are nothing but node numbers, right. You may recall numbers 1 to 5 refer to the zone centroid numbers and rest are referring to the road intersections, right. Now we find number 5 in this cell of the matrix. What is the designation of this cell? This cell is 1 6. So when you have a number, the first inference is that there is a connection between the nodes 1 and 6. There is a link named 1 6 or 6 1, okay. There is a link connecting 1 and 6, that is the first inference. Second inference is this number actually means the link travel impedance. To be more specific, this is the travel impedance for movement from 1 to 6, not from 6 to 1, okay. This is the travel time or travel impedance from 1 to 6, 1 6, clear. Of course, in this particular case 6-1 travel time also happens to be, if 6-1 is here, that also happens to be 5, but it need not be the same in all the cases. Now we have number 3 here. This implies what? What is the first inference? There is a link connecting node 2 and node 7, right, and the travel time for movement from 2 to 7 is 3 minutes. In the other direction from 7 to 2 is only 2 minutes, right. If you want, you can just look at the picture again and try to understand. 2-7 and 7-2, 2-7-7-2, there is a connection. In one direction we have 2 minutes, and 2-7 3 minutes, 7-2 2 minutes. Now you can look at the cell values and try to understand the representation of the network links and nodes in the form of a link array table. Are you convinced now that it is possible to represent a road network in the form of a simple link array table? It gives all the information that you get from a picture that we have seen earlier. Suppose we want to incorporate other attributes of the link, length of the link, capacity of the link, all these things can be included. For example, here 1-6, if you want to include capacity, you can say 5 comma the capacity value, right, and put one more comma and give the value for length. It is a notation you are giving, and your analytical program will understand what you really mean by these numbers. The sequence is fixed, right. You can fix the sequence and give whatever link attributes you want to give for a link, right. So this is what we have discussed. The same picture is represented in the form of a link array table, and so far we have understood how to represent road network in the form of links and nodes, and then how to represent the whole thing in the form of a link array table. Now we are ready to go further to actually assign traffic. Your traffic assignment should reflect the way people choose their route for travel from one zone to another zone, is not it? Your assignment process must replicate the choice process of route by the travelers. So it is better, or it is important to understand how people are choosing route for movement from one traffic zone to another traffic zone, right, the behavioral aspects with regard to route choice behavior. The key to assigning users on the network is the underlying behavioral assumption of route choice, because in 1952 Wardrop established 2 mutually independent principles of route choices, 2 important principles. According to the first principle, users choose the route that minimizes their own travel time. If there are 2-3 alternatives, they look at the travel time implication of each alternative and choose the one which has got the least travel time, right. According to the second principle, users distribute themselves on the network in such a way that the average travel time for all users is equal on each route leading from an origin to a destination. How it is possible? Let us say there are 3 alternative routes available for travel from zone 1 to zone 2. As per this statement, the users distribute themselves in such a way that the travel time almost balances, is almost same on all the routes. Let us say the free flow travel time along route 1 is 2 minutes, along route 2 2.5 minutes, along route 3 let us say 3 minutes. So, 3 alternative links may have 3 different travel times, but the users distribute themselves in such a way that the travel time equalizes. Is it possible? In practice, if more people are making use of the route which has got least travel time, the congestion will increase, resulting in increased travel time. Once it is congested, they get shifted to, part of them will get shifted to the next shorter route. Then in the process that route also will get congested, then there will be shift to the other route. So in the process there will be a kind of balance, so that the travel time implication on all the 3 alternative routes become almost same, right. So these are the 2 philosophies or concepts proposed by Waldrop. The first rule defines the user equilibrium, whereupon each user goes on the shortest path. So the nomenclature given for this particular concept is called user equilibrium approach. Clear? The second rule defines the system equilibrium, whereupon the total cost of using the system is minimized, total cost or travel time whatever is minimized. The terms shortest and cost typically refer to travel time in general, but elaborate equilibrium formulations account for generalized costs, which include not only travel time, also fuel consumption or simply cost of travel, fare price in the case of public transit, and so forth. So forth includes comfort, convenience, okay, safety and so on. If all these things are brought into route choice process, then you will be dealing with generalized cost of transportation, but it is very rare, maybe for research purpose people do with generalized cost of transport. In practice, travel time is taken as a basis for route assignment, because of the fact that the time implication for urban travel is not large. It ranges between few minutes to about 60-70 minutes in most cases, right. So there is no need to bring in all other related aspects like cost of travel, comfort, convenience and so on. A latest development in equilibrium principles recognizes the fact that users have only limited information about the network, and their transportation options, either mode or route, for going from an origin to a destination is based on the information they have. So when we talk about shortest route or minimum travel time, it is based on the assumption that every traveler is clear about the travel time implication along a particular path. In practice it may not be true. I may assume that taking Anna Salai to go to Central Station may take about 30 minutes, and she may assume that it will take only 25 minutes. So these are all perceptions, and thus it is more logical to base the equilibrium on the perception of users. This way each user assigns himself or herself on a path that he or she thinks is the shortest. This is called stochastic equilibrium, right. It is a stochastic process, quite random, based on the perception of individuals with regard to travel time. The effect of these 3 types of equilibria is most notable on networks. According to the user equilibrium, when we have different alternative routes, according to user equilibrium, all used paths between the origin and destination require the same travel time or cost whereas all unused paths have times that are greater than the shortest time. User equilibrium implies that every user is going to take the shortest path. If there are two shortest paths with same travel time, then both the paths will be made use of by the users. If there is only one path, then that is the sole route that will be used by all the users. Okay. That will be the effect in the field. When we have three alternative routes, you will find that only one route, which is the shortest, is used by everybody. Hence it is likely that several alternative paths between the origin and destination will not have any flow at all. If you assign traffic based on this equilibrium, you will not be assigning any traffic for other alternative routes, you will assign the whole of the traffic only to the shortest route. According to system equilibrium, all possible paths are evaluated and users are assigned in a way to minimize the network wide travel time or cost. There is a balance developed for the whole of the network. This equilibrium rule is useful during planning stage of large traffic studies, mostly not for transportation system planning, only for traffic studies involving signal timing, channelization exercises, lane allocations and other traffic elements which can be used to encourage or discourage particular routes, so that the network wide travel time and the resulting pollution or congestion level is kept at minimum. This assignment is mainly used for traffic management purpose, to balance the traffic flow in the network by some management measure, right. According to the stochastic equilibrium, all reasonable paths, what do you understand by reasonable paths? In the perception of the users, whatever they feel reasonable, between an origin and a destination will have traffic flow. Often the user equilibrium is considered as the basis for route assignment. User equilibrium is the sole basis considered for route assignment. Hence the first step in the process of route assignment becomes the identification of the minimum path or shortest path from zone centroids. Why? Because as per this equilibrium, we assume that all the users will use the shortest path. So it is important for us to know the shortest path from a zone centroid to all the points of interest. Points of interest are the centroids of other zones. So that is the first step as per the user equilibrium principle. Now how to find out the minimum path from a zone centroid? The minimum path may be that route of travel which has the least accumulation of time, distance or other parameters, more commonly time. The sequence of nodes which defines the links comprising the minimum path from a zone centroid to the other points of interest, nodal points in a network, is called tree. You just trace off the minimum path and it will go through a number of nodal points. So this complete set involving a set of links and nodes is called a tree. The tree is determined by starting from the zone centroid and progressively selecting the shortest path to the other nodal points in the network. Obviously we start from the centroid and progressively add the cumulative time to get the shortest path information. Let us consider this simple example. The network shown consists of a zone centroid, 15 because you can see the dotted lines connected to number 15, right, and a number of nodes and links. The question is, or the problem is, to build the minimum path tree from zone centroid 15. There are no other zone centroids shown here, right. We are just taking a small segment of the network connected to one zone centroid here, right, and trying to understand the principle of minimum path tree to reach out to all the other nodes, right. And we will see how to go about doing this exercise in the next class. To summarize what we have seen now in this class, we started our discussion with regard to representing road network using nodes and links, and we understood clearly how to represent zone centroids with node numbers and how to connect zone centroids with dummy links. And in this regard we need to remember that zone centroids should not be connected directly to the adjoining nodes by dummy links, they should be connected to only the adjoining links and in turn connected to the intersection nodes to avoid the problem of unrealistic analysis of intersection traffic flow. Then we discussed about representing the network in the form of a link array table, right, and now we are clear that it is possible to represent the whole of the road network along with the attributes of the link, right, in the form of a link array table. Then we discussed about the principle followed in route assignment. In that context we discussed about user equilibrium, system equilibrium and stochastic equilibrium, and finally we understood that user equilibrium is a principle normally adopted for route assignment. This implies that there is a need to identify the shortest path from the zone centroid to all other nodal points if we are going to use user equilibrium for route assignment purpose, and we will proceed with this process in the next class.